J'ai une test, oui, yes, it works.
Hi everyone, so welcome back to the Early Mars climate modeling session. I hope you all had a very good lunch. I think the temperatures in this room are evolving more or less with the Martian climate. I'm going to hand it over to Frederick Schmidt, who's going to talk about ancient Martian climate with a polar ocean and ice sheet dynamics. When you're ready.
Thank you very much. So I'm happy to start this afternoon session with this controversy of the ocean on Mars. So I have to start by thanking all my co-authors. So Igor is here in the room, so if you have any question, we could, of course, ask him also. So just a few words about this ocean on Mars. So it all started in the 90s with the identification of coastal geomorphology by Parker, a collaborator. And actually, two contacts were identified. The contact number 2 has been identified to follow the gravity equipotential, thanks to the MOLA data. And the mean elevation is around minus 3,900 meters. And there are plenty of work trying to put an age on this ocean. And so here I put, for instance, an age from Ivanov at 3.6 billion years ago. And in recent years, this story of the ocean on Mars has been renewed with two independent studies. So one by Rodriguez and collaborator, and another one by Cotard and collaborator. And they both identify near the shoreline some very peculiar terrains that they call sun-print terrains or run-up. And actually, these terrains are indicating that flows are going uphill, which is very strange. Usually, flows are going downhill. And they identify this as potential tsunami deposit. And then, of course, it's an indirect indication of the ocean. And then they try to find what could be the source of this potential tsunami. And the Cotard group identified the Lomonosov crater, which is a nearby crater with very peculiar depth to ratio shape. And so they proposed this as the source of this tsunami. And they made a numerical simulation of the tsunami wave, and the wave seems in agreement with the shape of the sun-print terrain. So this, I would say, relaunched this question of about the ocean on Mars. There have been a lot of controversy. I just put here for you some of the papers that put the paradox of this ocean, and especially, I didn't mention that, but we could date this Lomonosov crater at 3 billion years old, so quite recent one. So if I summarize this paradox, so this has been discussed by Turbet and Forget in a previous paper. If there's not enough greenhouse gas, of course the ocean should freeze and there's no ocean. But if there is enough greenhouse gas, then a lot of rainfall are expected, and we don't see that much valley network. But also the evaporation of the ocean is very high, and then the water is stable in form of ice in the island, and so ice should be accumulated in the island. So to bring some clues in this perspective, in 2022 we proposed a coupled atmosphere and ocean model, so using the Rocky 3D model for the GCM and combined with the Socrates radiative transfer scheme. And we fully coupled this with a dynamic ocean. At this time, we use a simplistic ice sheet return flow to estimate the mass balance of the ice. And so this is the experiment we made. So we took the current topography, we removed both caps, we set the shoreline at minus 3,900 meters, we set 1 bar of CO2, and it was 10% of H2 at this time. But now we use this collision induced from Martin Turbet. He just had a presentation about that before the lunch. And so now to have the same efficiency, we need 22% of H2, and this is exactly in agreement with what has been published by Kamada and collaborators. We set the obliquity at 40 degrees because 40 degrees is the most common value at this time from the paper from Lascar. And with this previous work in 2022, we could find that the ocean is stable, but of course with condition, with a mass flux of the ice sheet 10 to the 15 kilogram per year, then everything is in equilibrium. Of course, this looks as a huge number, but we can compare this with, for instance, the latest glacial maximum on Earth, that was actually with more than 10 to the 16 kilogram per year. So it's something feasible, huge, but feasible. So what are the outstanding questions I would like to address in this talk and in the paper that is related to that? So what is the total volume of the water required? And what is the shape, the flow of this ice sheet in this cold, wet environment? And for this, we need to couple our ocean and atmosphere with an ice sheet model. So this is what we did. We used the Grizzly model to solve the Glen flow equation in Cartesian coordinates and in equi-era projection. We used the accumulation as a positive degree day scheme. And then, of course, we combine and take as a boundary condition for the Grizzly model the GCM, so the temperature and the accumulation from the ice sheet model are actually coming from the Rocky 3D GCM. And then we did an asynchronous coupling. First, we start with Rocky 3D, and then with Grizzly, and then Ready to Rumble. We go back and forth, one after the other. And we can only estimate with this asynchronous coupling the equilibrium states. So that's the whole point of this study. Of course, the dynamic timescale is very different. It's only 100 years of simulation on the atmosphere and ocean to reach the equilibrium, because the timescale is much shorter than for the ice sheet. For the ice sheet, we need to run it for 400,000 years. And we call this RG, the number of time of this coupling. And at the end, we can estimate this equilibrium state. And so this is the results. This is the results at the starting point. So this is exactly the same as in the 2022 paper. So we can estimate the ice snow fraction at 40 degree obliquity. But then, after few steps of coupling, we can clearly see that there's a development of an ice sheet in the Tarsis region, as expected. And so we zoom in this particular region. So what you see here, the white outline here, is exactly the region where we focused our Grizzly, our ice sheet modeling. So I will present you some of the results now. So you see here the ice sheet mass flux as a function of time for the 3 steps of the coupling. What is interesting is that the equilibrium seems to be reached after hundreds of thousands of years. And you see at the end the equilibrium because the gain and loss are more or less compensated. And then we can estimate the ice sheet flux, which is on the order of magnitude of 10 to the 15 kilogram per year. So this was in agreement, actually, with our previous estimate with the simplistic scheme. And what is interesting is that this time scale is actually a time scale that has been also proposed in a previous paper this year of the transient event of H2. So if you have H2, we can have it in the atmosphere. It can be stable for a few hundreds of thousands of years. So this seems in agreement, or at least the H2 seems to be long enough in the atmosphere to make this equilibrium. So this is the results now for the surface and the volume. So we estimate a surface around 30 10 to the 6 square kilometer, and the volume that is equivalent to 350 meter global equivalent layer. And this is almost the equivalent of the ocean. So basically, if the climate is stable with an ocean, we need almost the same amount of water in the ice sheet to be stable. We did some sensitivity tests. For instance, we changed the basal drag, the different melting coefficient to see what is the robustness of the results. And so you have here this table that's summarizing everything. So basically, the volume seems quite consistent, whatever the parameter, and the change is mostly in the extent that can change up to 20%. So going back to the maps, because this is what we are also interested in. So this is the results after the coupling of the ice in the ice sheet around the Tarsis region. And you see that the accumulation, of course, is near Tarsis, and it can reach an altitude up to 15 kilometers. And this is the thickness. Actually, the thickness can go up to 4.3 kilometers, and we include here the crust isostasy, because the rebounds of the crust makes the accumulation larger, so we take this into account. And yes, the accumulation is near the high altitude and the flank of the volcanoes. We can also estimate, of course, the flow and the direction of the flow. And so this is what is plotted here. And actually, we found speed as 1 kilometer per year, which is quite fast. But this is only in the region, in the lowest region, where the temperature is the warmer, in the edge of the cap. And one interesting point here is that part of this ice tongue is directly going to the ocean. So it means that for the flux going back from the ice to the ocean, at least a part of it is directly refilling the ocean. What is interesting is that one particular valley that is called here Casei Valles was expected to be one of this remnant glacier tongue, but here in our simulation, it seems that there are no prediction, I would say, in this Casei Valles, which is a bit puzzling. But I think the reason is because this valley is too low in altitude, at least in the topography that we have used. And so most probably we would like to now test other topography to try to see what is the topography compatible with this Casei Valles let's say glacial tongue. So as a conclusion, we set a fully coupled atmosphere, dynamic ocean, and asynchronous ice sheet modeling. We found that the cold and wet regime is compatible with an ocean with 700 meter global equivalent water. It's almost 2 times the ocean. It's compatible with geological record, but no perfect match, for instance, the Casei Valles. And so it opens the question of what has been the topography at this time. Of course, we would like to study the stability in, let's say, more test other possibility in a parameter space to have this stability. And of course, the remaining question is where is the water now? It has been escaped. So we have seen that from D to H, only a 100 meter gel has been probably escaped, and here it's clearly much more. So I would be happy to take any question now, and if you need more details, there is this paper that just came out in GJR Planets. Thank you for attention.
So we've got some time for questions.
Okay, I have the question on the second point. So just to make sure I understood, what happens if you have less than 700 meter gel? That means all the water is trapped in in the form of ice?
So that's a good question. Actually, we didn't limit the total amount of water in our simulation. So we cannot really say that if we limit where the water is going. But we did an experiment. I have some extra slide. Actually, it's in a paper. Yes, we tried to lower the water level and to see what's going on. And so this is exactly the same kind of results, but instead of having the regular ocean, we just diminished by 15, 30, and 50% the volume of the ocean. And I guess this is going to your question. So the volume, I have to check exactly the number on this, but I think it's more or less the same. So the volume of the ice sheet is more or less the same for each of these experiments, but the total volume of water is of course decreasing. So it means that it goes in the ice sheet and the ocean, but we need this loop to refuel the ocean.
I have another question, unless someone wants to.
Yeah, no problem, of course.
So I had another question on the plot where you showed the ice flow.
Yes.
Could you show it again?
Yes, this one.
I wanted to understand. So if I understood correctly, the part of the glacier on the north is refilling the ocean.
Yes.
What's happening to the part of the water that is melting in the south? Where is
yeah,
the
sure. So the topography, as I mentioned, we can go this one, is more, it's an ice sheet, it's a cap, so it's going outwards, of course. So in the south, the flow direction is going to the south. And of course, this water then melts. This is the point of this modeling. It should go back in the ocean, but
in your model, what do you do? Do you put it back in the ocean, or do you simulate actually the flow of this liquid water?
So as I so in the ice sheet model, there are no flux of water going back to the ocean. But in the GCM, we just take the amount of so let me think about it. To answer precisely, for sure, the melting is not following any streamline. There are no streamline at the edge of the south region. So clearly, there are no way to force the water to go back to the ocean that are here from the topography itself. So this is for sure. I think, yeah, maybe Igor would like to comment on that. So I think it's simply the melting of this water that is going back to the ocean. This is the idea. Anyway, Igor, I'll let you answer. It's not working. You can use this one.
Yeah, GCM basically is kind of decoupled from the ice sheet. So I mean, we use ice sheet as a boundary condition, but it's not like we're doing back and forth. Well, I mean, we do back and forth interactively, but only as a boundary condition. So when we run GCM, we actually assume that the system is already in stable condition. So whatever we accumulate over the ice sheet, we put into the ocean back, assuming that there is a flux to the ocean. So then on the ice sheet part, basically we accumulate ice as to the point when basically there is similar flux back to the ocean. But basically GCM just uses implicit way to put water back. So basically everything that is out of balance just distributed back to the ocean. That's basically how it works.
Hi, Samantha Baker, Caltech. Possibly a naive question, but my understanding is that we have geomorphic evidence for glaciation at Tharsis. Do we need to invoke an ocean in order to produce that, or do we have other, like, is it difficult to produce that amount of glaciation without an ocean, and therefore we're like trying to find things like an ocean, sort of these maybe more extreme conditions that could have produced that, or are we capable of producing the amount of glaciation that the surface represents without an ocean?
Of course, we need evidence of this glaciation at this time. The difficulty, I put this plot, so it's coming from the 2022 paper. Most of the region here has been recovered by Amazonian terrain, so much more recent terrain. So because of the volcanic activities, and so because of that, it's not that easy to find a glaciation from this age. So one good candidate is the Casei Valles, so that's why I focused on this one. But unfortunately, from the topography, at least the field we used, we don't really predict an ice sheet in this particular region. So this means that maybe the topography has been different, or the volcanic material just recover everything, and we don't see that anymore today.
Okay, awesome. Thank you so much.
Thank you.
Thank you very much, Frédéric. And so now we're going to move on. Are we doing applause? I don't know. All right, fair enough. Okay, so now we'll move on to Alex Gauvin, who will be talking about constraining early Mars climate through coupled hydrological modeling and comparison with geomorphological evidence.
Hi everyone, I'm Alexandre Gauvin from LMD, and today I'm happy to present a new global hydrological model to constrain early Mars and its climate, and use geomorphological evidence to do it. So, some word of context, my work is a part of Mars Through Time ERC project, and the objective of this project is to develop a numerical model to simulate the past environment, and in this context we create a planetary evolution model to couple multiple model with a global climate model. So I will not present in detail the planetary evolution model, but Jean-Baptiste Clément will do it this Thursday. And my work focuses on the hydrological part of the planetary evolution model. So on Mars, there is a lot of morphological evidence, and we would like to use it to constrain the global the climate of early Mars. And to bridge the gap between the climate and this geological evidence, we need a high-resolution hydrological model. And I will present this model now. So just to mention, we have submitted our paper this last week, so don't hesitate to check it on GMD. It will be available soon, in few days, I think. So don't hesitate to check it if you need more details. So to present our model, we want to simulate ocean, lake, and the connection between this water reservoir, and estimate the river discharge. And we want a dynamic system to remove or recreate this water reservoir. And as I said before, we want to compare our model with the geomorphological evidence. So we need to keep a high resolution, but we need to also have a low computation time. So to do that, we compute our model at watershed scale, and we have post-processing to create the high resolution result. Our hydrological model is divided in 2 steps. First, we create a hydrological database, and then we use this hydrological database in the hydrological model. So first, our model, to create this hydrological database, we will analyze this. We'll analyze the molar topography or topography, and for each pixel in this digital elevation model, we can compute the flow direction on the DM following the steepest slope, and identify the local depressions and extract the watershed of each depression. So on the right, you have an example with 4 local depressions. And after that, we can create a graph, a binary tree, where, and in this graph, we will find the spillover point of each depressions and find the link with the downstream depressions. And after that, we can build the graph as on the right. On each node in this graph, we can compute informations and functions like maximum water volume or watershed area, and a function between the elevation, the volume, and the area of the lake. And we save all information in this NetCDF database. In this presentation, I will talk about on 2 topography. First, we apply our methodology on the molar topography present by Mars. In this topography, there is 1 billion cells, and in the hydrological database, we found 12 million depressions. And we also compute this hydrological database for pre-true polar wonder from Boulet et al. You can see an example on Gale crater. On Gale crater, we found 10,000 depressions, and you have an example of hydrological functions for the white for a random depression in this area. After that, we can use this hydrological database in the hydrological model, and we use an existing model named fill spill merge. So first we will in the hydrological model we will fix a global equivalent layer and an evaporation rate, and we will iterate this scheme until we reach a steady state. So the evaporated volume is a function of the evaporation rate and the lake area, and the precipitation rate depends on the evaporated volume divided by the total area. And then we can re-inject the precipitate volume on the hydrological model. And we iterate this scheme until we reach the steady state. We ran, to explore our model, we ran 48 simulations with different evaporation and global equivalent values. And we analyze 3 initial states. Here you can see an initial state for a global equivalent layer of 100 meters. So you can see this 3 initial states on the left, and we ran these simulations for 100,000 years, and we can see on these plots we reach the same steady state, and for a constant precipitation evaporation ratio. We have a stable lakes and ocean. So we have no sensitivity to the initial states, and the steady states depends only on the global equivalent layer. now we can analyze the model output of our model. Here you have an example for a global equivalent layer of 100 meters, and we can see an ocean on the north, and for this example, if we analyze the water distribution according the latitude, we can see there is 50% in the northern of the total of water in the northern lowland, 20% in the low latitude, and 30% in Elias, Argyll, and mid latitude. We also run the model for the pre-true polar wonder topography. And we can compare these two topography with this figure. The main result on this figure we can see on the right, the water storage of the Northern Ocean moved to lower latitude and Elias. It's the black area for early Mars, and the blue and orange area are for molar topography. And if we look the longitude, the relative volume of water according to the longitude, we can see a lake between minus 60 and 60 degrees. And this lake is due to there is no crater in this area, and we can't store the water in this area. So with this result, we can say we need a high resolution topography map of early Mars to create a good representation of the water distribution on the planet. Another model output, it's the river discharge or water outflow. It's for the same simulation with a global equivalent of 100 meters. On this plot, we can see four main rivers, mainly due to the steep slope influenced by Tarsis. And if we zoom on J0 and Gale crater, we can see the confluence of two rivers, as we can see on the observation. We also create a post-processing to transform our model output to a valley network, and to do that, we want to compare our result with the observations, and we create indicator to constrain the model. So we would like to compare with the open and closed basin lake. For this simulation, we can see that the Gale crater overflow on east-north, and on the observations, we can see that the Gale crater is considered as a closed basin lake. So our simulations have in crater there is too much water inside. And we would like to also compare the valley network, the delta, and the shorelines. In this surface model, we don't take into account the infiltrations. So to create these infiltrations, we create a groundwater flow model built with ModFlow 6, developed by USGS. And to run this model, we need an input, the aquifer recharge. This aquifer recharge is given by the surface model. And the model output is given by this groundwater flow model. It's the aquifer discharge, and we can create an aquifer discharge when the water table elevation intersects the topography. To set up this model, we need key parameters: aquifer thickness, specific yield, aquifer porosity, and hydraulic conductivity. So, in conclusion, we have developed a hydrological model at global scale with a high resolution with acceptable computation time to simulate ocean and lake and river discharge. This model is still under development. We are currently couple this surface and subsurface model. There is limitations in this model. We use actually the current topography, but we would like to create high resolutions topographic map of early Mars. And then the big next step is to couple our model in the planetary evolution model to link the climate, the hydrology, and the geology. Thank you for your attention.
Okay, so I think we have time for one question.
Hi, very nice work. Just one comment. Apparently, you didn't remove the northern and the southern cap. There is a reason for that?
No, there is.
Okay, no problem. I think it's a minor point. Yeah, I have a question about the comparison of the network of your model and the network in real life, in the topography. So what is your starting point? Because if you start with the current topography, actually, it's not really independent of the network. So how would you solve this problem?
We would like to use the hydrological database and remove some craters and add erosion rate or something like that to recreate this valley network. But it's a lot of work to do that. But yes, we would like to add an erosion processes in our model to recreate this.
Or I guess to start with something smooth.
Yes.
And let's let this grow with time. Okay. Yeah. Thank you very much.
Okay, make it quick, please.
Just a comment that all this story occur in the same time as bombardment. And your two extreme case of pre-Tarsis topography, that is not ideal because you don't have the cratering. That's what you that's why it's not solved. And the current topography, it's 4 billion years of impact cratering. So that's really what is missing in this model. That is the regular bombardment activity.
Yes, sorry.
It wasn't quite a question, okay. More comments that, what you really need to add is sort of a regular bombardment activity.
Yeah. Thank you.
Thank you very much, Alexandre. And next we have Maxime, who's going to be talking about not enough H2O2 to warm early Mars.
Okay, hi everyone. So I'm a former postdoc on the Mars Through Time project, and I'm going to convince you today that H2O2 was not the solution to the faint Youngson problem on Mars. And to do that, I will start setting up my timer, because I don't want to take too much time. I'm not going to spend too much time explaining what's the faint Youngson problem on Mars, because I guess we're all more or less on the same page. I'll spend a bit more time telling you how people came up with the idea that hydrogen peroxide, H2O2, could be a solution to it. Then I'll tell you how we endeavor to test this assumption using the climate and chemistry model that we have at LMD. And finally, I will present another way in which it could have been a solution, but it's also not working in this other way. But yeah, so very briefly, the faint-Youngson problem on Mars, where, as we've been hearing since this morning, early Mars, especially in the Noachian, was potentially just episodically, but at least for some time had liquid water, etc. And we don't really understand what could have caused the warming. And recently, people came up with the idea that the greenhouse effect induced by H2O2 could be the solution. That was first proposed by a Japanese team led by Yuichi Ito in, I don't remember whether that's 2021 or 2020, but anyway. And that was later checked, also confirmed by a team led by Jorge et al. 2024, where in this paper they study a list of possible greenhouse gases, and they shortlisted 5 or 6 of them, I think, which have the greatest potential, and H2O2 was had the best potential to warm up early Mars. Why is it? Well, it turns out that H2O2, as you can see here, I don't know if it's going to work with the, yeah, exactly. H2O2 has an absorption window around the peak emission of a black body between 200 and 270 Kelvin, which makes it a very good greenhouse gas to warm up Mars. Using radiative models, these two studies kind of converge towards the results that in a early Mars atmosphere you would need about 1 ppm H2O2, this blue curve here, to reach the magical 273 Kelvin. So that calls for the question, is that possible to accumulate in 1 ppm H2O2 in your atmosphere? To this question, Ito et al. Answered yes, and they obtained these results by assuming that H2O2 was the main agent of CO2 restoration. Well, now that might sound a bit complicated, say like that, and that's the reason why I will spend a bit more time elaborating on this question of CO2 restoration. So in a CO2 atmosphere, if you have a star, then you will receive light from it and you will start photolyze your CO2 to CO. And if nothing else happened, then your CO2 atmosphere will turn into a CO atmosphere, which is not what we observe. So something else must be replenishing CO2. And you might say, well, this something is just taking the pieces and putting them together back. But it's not that easy, because actually this reaction is super slow. It's been forbidden. So you have to figure out some other ways to do it. On present-day Mars, other ways involve this cycle of reactions. So we call it a catalytic cycle because it yields this net reaction, which is pretty simple, but involves a bunch of other species, which we call catalysts. And here that's essentially hydrogen, atomic hydrogen, OH, and HO2, which are the catalysts. So on present-day Mars, I think this cycle is responsible for about like 80% of CO2 restoration. And there's a few other cycles, and one of them involves H2O2. And on present-day Mars, it's responsible for about 8% of CO2 restoration. Well, what Ito et al. Suggested was that on a warm and wet early Mars, you could have much more H2O2, so that this catalytic pathway could be much more important. And based on the assumption that it would be responsible for 100% of H2O2, of CO2 restoration, they were able to equate the H2O2 photolysis rate with the CO2 photolysis rate, and based on that, calculate an abundance for H2O2, which they claim was sufficient to yield a greenhouse effect that would warm up Mars. So this reasoning is based on a fairly strong assumption, namely that this pathway is responsible for 100% of CO2 restoration, and that's exactly what we decided to test properly using a climate and chemistry model. So the approach we took was to test in a most favorable case, actually, whether we could at all accumulate 1 ppm H2O2, and if we cannot, well, then the job is done, and H2O2 is out of the picture. So we selected this, we built up this most favorable case as being an already warm and wet early Mars. And we also neglect all the sinks for H2O2, namely surface deposition, condensation, etc., etc. So this already warm and wet early Mars, we got it from the simulation that Martin presented this morning, where we already have a surface temperature above 273 Kelvin that we obtained for a 2-bar atmosphere and a fairly large amount of water, 550 meter GEL. And to this simulation, we add a CHO chemical network. So you may remember that in Martin's simulation, the reason why it was hot was that there was 15% H2. But here, we merely use it as a radiative trick to warm up our atmosphere, so you can forget about that, because from the point of view of chemistry, that's just going to be a 2-bar CO2 atmosphere, and hydrogen will be provided to it through the water cycle. All right, and what we did also was to run both 3D and 1D simulation, because 3D simulations yield a much more accurate water cycle, but they are really time-consuming, and when you are running for the chemistry, sometimes you need very long simulation time. So we run both 3D and 1D and compare between them, and once we're happy with and find that the 1D is reproducing the 3D, we run the 1D for much longer to see what's the equilibrated chemical state. So here's an initial comparison between the 1D and the 3D to convince you that 1D is doing a pretty good job. Here you have the temperature profile, and here you have the water content. And then we ran the 1D simulation for much longer, as I said, to equilibrate chemistry, and that's the result. So here, thin solid lines are the 1D, thick solid lines are 3D, so you see that the match is pretty good, and the dotted lines are the 1D simulation after 1,000 Martian year evolution, which yield converged chemical states. And when you look at H2O2, you do see that it builds up to about 20 ppb, which is much less than the 1 ppm abundance that you would need to have a significant greenhouse. So from that we can, which is this line. So from that we can conclude that, well, it's actually not possible to have enough H2O2 in the atmosphere of early Mars to yield a greenhouse effect which is large enough to solve the faint young sun problem. We wanted to dig a bit deeper into what's happening in the chemistry, and we figured out that this pathway is actually not responsible for 100% of CO2 restoration, as was assumed by Ito et al., but it's responsible for about half of the restoration of CO2, which is still much larger than it is on present-day Mars, and that makes sense because the two atmospheres are pretty different. And this pathway, which is responsible for 80% of CO2 restoration of present-day Mars, is only responsible for about 40% of its restoration on a warm and wet early Mars. Okay, now, so we don't get a long-lived warming thanks to the greenhouse effect of H2O2. There was still one chance for H2O2 to stay in the picture, and that was if we had a transient burst, transient release, massive release of H2O2, and that could be the case. It has been posited, for instance, that on the Earth, during a snowball Earth episode, H2O2 dissolves in the ice cap, and when the ice cap is destabilized, then there's a massive outburst release of H2O2 in the atmosphere. If a similar scenario happened on early Mars, then maybe that could be a way to have enough H2O2 to warm up the atmosphere on an episodic, in an episodic manner. So we also endeavored to test that by, again, taking an approach where we would check in the most favorable case to accumulate H2O2 if that's possible or not. So this most favorable case would be if we maximize the H2O2 content in the ice cap. So for that, we considered the highest H2O2 content in the air, which is what we calculated in the simulation that I just showed you, and the highest partition coefficient between air and ice for H2O2. And the second point is we need the quickest release of H2O2, which corresponds to the quickest destabilization of the ice cap. And in this case, we considered that all the flux that we receive is used to melt the ice. And in this case, which yields a fairly theoretical and unrealistic case, but the most optimistic on the point of view of H2O2 release. And we restarted our simulation, putting the corresponding H2O2 flux in the atmosphere for the time it would take to destabilize the ice cap. And that's this blue shaded area. And you see that indeed, in this case, the H2O2 abundance skyrockets. It even reaches up to about 10 ppm. But as soon as the flux is exhausted, because you have melted all the ice cap, then it starts going down again. And all in all, you never exceed this magical 1 ppm for more than 150 sols. And if you consider a slower destabilization of the ice cap, like 10 times slower, for instance, you never quite get to the 1 ppm. So it seems that even in this case, you only get a few hundred sols of warming by H2O2, which is also not compatible with the time you need to create the river. So based on that, H2O2 seems to be, at least H2O2 alone seems to be out of the picture. And so that prompts us to encourage looking for other solutions. And with that, thank you for your attention.
Okay, anyone?
Jim Head, Brown University. Excellent talk. Thanks for exploring this in excruciating detail. It's really important. I would just encourage you to think a lot about the 151 sols. In a paper we did, Pastuck and Head 2015, we looked at the amount of time it would take to melt an ice sheet in the southern uplands. And, you know, over one summer season, okay, or even less than that, you actually get enough water produced to fill all the open and closed basin lakes. So this is really promising. I agree with your overall thing, but this is really promising for the short-term aspect. So I'd encourage you to do that as well.
Well, thank you for these comments. Actually, I was this morning when I was hearing all your talks, I was reconsidering about that and questioning how relevant this timescale would be. Well, actually, once again, this is not really a realistic timescale because that's very back of the envelope calculation, optimizing making it as short as possible for the destabilization time, because that would mean basically that it takes, in this case, it takes about 80 sols to melt a 550 GEL ice sheet. So, that's pretty quick.
I'd like to introduce another concept here. I should have done this in the morning. I would appreciate it if people would stop calling these rivers, because in fact, they're not flowing all the time. I suggest we call them arroyos, which is a Spanish term for transient events that the river bed is dry most of the time, okay? And it's only intermittently flooded. That's why when you're a camper in the Southwest, you don't bed down in an arroyo because there's gonna be rain in the mountains and you're gonna get drowned. So that's the way it works there. And I think that's could be, with these short-term things, better term might be arroyos, because we know they're mostly dry today and way back into time. So just not a negative comment for you. I think it's just a promising comment, because maybe this is enough.
Thanks.
From Turku University, and I'm going to talk about organic matter formation from formaldehyde on Mars through time. So as discussed so far, early Mars was quite different from the present Mars. For example, the atmosphere was thick, about 0.5 to 2 barrels, composed of mainly by CO2, and also a few percent of CO and hydrogen, which is supplied by meteorite or volcanic degassing. And also, we agree the surface liquid water, but however, to understand the habitability of early Mars, we need to know the availability of biologically important molecules. So organic matter. So for observation, we know that organic matter have been detected at Gale and Jezero crater recently. And interestingly, Curiosity rover detected a wide range of carbon delta 13, which is around like minus 130 to 20 per mil. So which is quite depleted in carbon 13 compared to like previously detected organic matter. So the question is, what is the origin of this organic matter? So here is the two questions I'd like to answer in this talk. So first one is how much prebiotic molecules were available on early Mars, and also what is the origin of the organic matter. So to answer this question, I focused on the molecule formaldehyde, which is H2CO. And why is this molecule important? This is because the formaldehyde is a precursor for the biologically important molecules such as amino acid. Amino acids could be synthesized from the sterical reaction or formose type reaction. And also, the sugar could be formed from the formaldehyde. So when the formaldehyde is in water, it starts to polymerize to a heavier organic matter, which increases the sugar, such as ribose, which is, as you know, a component of RNA. So that's why this molecule is very important to understand the origin of life. So determining the availability of formaldehyde on early Mars is very important to understand the prebiotic chemical evolution to the origin of life. So how the formaldehyde is formed in the planetary atmosphere? So if we assume the CO2 atmosphere, when first the CO2 is photodissociated into CO, and water is also photodissociated, and the products of CO and hydrogen atom react to transform to the HCl, and these HCl combine together to form formaldehyde, and which is then deposited into water. And as I said before, this formaldehyde in water would be polymerized to organic matter. So in these processes, there's an important isotope fractionation happening during the CO2 photolysis. So 12 carbon CO2, so the light CO2 is more efficiently dissociated than heavier CO2, which means the product CO would be depleted in carbon 13, and this depleted CO would be included in formaldehyde, and also the water in formaldehyde, and finally also in the organic matter. So let's move on to the question number one: how much prebiotic molecules were available on early Mars? So to answer, we calculate a global average production of formaldehyde. So here's the method. We basically use the 1D photochemistry model. I'm not gonna talk about details, but this model solves the photochemical reaction and the diffusion at each plate and gets the average atmospheric composition. And we also assume escapes of the hydrogen, oxygen, and carbon, and also the deposition for formaldehyde and volcanic degassing. And for the atmospheric assumption, we assume 2 bar CO2 atmosphere with a few % hydrogen and CO, and as the same as previous talk, I assume the CHO-bearing species and solar UV flex at 3.8 billion years ago. And lower right panel is an example of the output of my model. So we can get this kind of average profile of the atmosphere. So this is the main result and of the formaldehyde deposition with various CO mixing ratio and the hydrogen mixing ratio. So the CO and the hydrogen mixing ratio is not constrained on Arimert, so I varied these 2 parameters. So as you can see, formaldehyde increases with hydrogen mixing ratio, and also let's look at the CO 50%. In the CO-dominated atmosphere, formaldehyde is continuously produced. And for the hydrogen mixing ratio, there's a boundary of 0.1%. So if there is hydrogen above 0.1%, there is a continuous production of formaldehyde. So in warm climate, which is orange square, so formaldehyde deposition would have 3 times 10 to the 9th per centimeter squared per sec. And this corresponds to the production of ribose in the ocean, about 4 times 10 to the 4th kilogram per year, using previously reported conversion rate from the formaldehyde to the ribose. So this is the production of formaldehyde on Mars history. So for the Noachian and Hesperian, if there is active volcanic degassing, so which means there's enough hydrogen, in that case, the large atmospheric production of formaldehyde continued. And after that, volcanic degassing decreased with time, and probably in Amazonian, volcanic degassing would have decreased compared to the Noachian, and in that case, the production of formaldehyde would be low. So this is the answer. So for the question 1, how much prebiotic molecules were available on Arimert? So for the sugar, there would be a continuous supply in the warm climate in the late Noachian. And also, this is the average, and global distribution of formaldehyde will be discussed in the next talk by Arihiro. So for the question 2, what is the origin of the Martian organic matter? So we include the carbon 13 in the model and compare with the measurement by Curiosity rover. So to do that, we have developed a coupled photochemistry and climate model. So the photochemistry model is the same as the previous one, and except I included the carbon 13 in the model. And for the climate model, I used 1D line by line radiative convective code by Wadsworth et al. Group. And I created a lookup table of the temperature profile for surface pressure and also the CO2, CO, and hydrogen mixing ratio. So this is a calculation flow of the model. So we start from the initial conditions of 30% CO2 and 69% CO and hydrogen 1%. And surface pressure is varied from 0.5 to 2 bars. And initial carbon isotopic value is minus 25 per mil. So I start from the photochemical calculation at 4 billion years ago and runs for 100 million years and up the temperature and photochemical calculation again, and until 800 million years. So this is a result, and also please look at the middle panel first. So we start from the CO-dominated atmosphere, and it changes from the CO to a CO2-dominated atmosphere. Here is why. So when the CO2 increases, as you know, the temperature increases by CO2 greenhouse effect, and then the water vapor increases in the atmosphere. And then increased water vapor photolysis leads to more hooked species, which enhances the CO2 recombination. So what about the isotope ratio? So the upper panel is calculated carbon isotopic ratio. So it starts from the minus 25 per mil, and it decreases with time, and it ends up with minus 200 per mil, which is very depleted in carbon-13. So why? So over time, CO that comes from the CO2 photolysis, which is depleted, increases with time. That's why the CO decreases with time. So here is potential sources of organic matter, and the blue line is the range calculated in this study from the formaldehyde, and curiosities has a wide range, and there's also the meteorite and igneous refractory carbon as a potential. So we suggest that for chemically produced formaldehyde would explain the strong depletion in carbon-13, but however, formaldehyde itself cannot explain the sources, so the mixing with the other organic matter is the origin of organic matter. So here is the summary of my talk. So for the question 1, availability of biological important molecules, there's a continuous supply of formaldehyde in the late Noachian, and also for the origin of organic matter. For the depletion, formaldehyde origin organic matter could explain, and also there would be multiple sources for the origin. If you are interested, please check my paper published last year. So thank you for attention.
Anyone got questions? Please come to the front. The mic is now working. Oh, okay.
Bethany Ellman, University of Colorado. So thank you. I think the finding of the organic matter by curiosity with the curious isotopic ratio is actually really important in terms of illuminating most likely not life, most likely, as you point out, the atmospheric photochemistry. I think one thing I didn't quite understand is sort of exactly how atmospheric pressure and water vapor play off against each other. Could you perhaps say again, so if the atmosphere was on the thinner side, say hundreds of millibar, at at the time of Gale Crater, how does the amount of water versus CO2 in the atmosphere control either the isotopic ratio or the production? Is there a difference or a testable there that we can look at? Because of course in situ with the SAM instrument, we can actually measure both the carbonate isotopic ratio that's in that same age material. I see ALH is compared there, but actually there's also the in situ carbonate C13.
Right.
So can you comment on what things could be tested with regard to water vapor and CO2?
Yep. So it's a very good point. And here there's 3 lines and dot and dash the just a line. So this is I didn't mention, but this is for the 0.5 bar and 1 bar and 2 bars. And as you can see, as the atmosphere gets thinner, the carbon isotopic ratio increases. It goes to like not to like depleted. So so if you like measure the carbon isotopic ratio, it might be the constraint on the atmospheric pressure. So that's the, I think, the connection between the CO2 atmospheric pressure and also the isotope ratio.
And is it just coincidence that the thickness of the bar, sort of if you translate it between the models, is about the same? Like you could.
Could you say that again?
Maybe I'll find you at the break. It's
okay.
It's a little complicated. It's interesting to me that each of the models, the offset in the delta 13C is about the same. Like if you take the 0.5 bar set of lines, it seems like you're just translating
you mean
the difference between the CO2,
CO2
and the HCO2.
Yes.
And I was making the point that we actually have the carbonate measurements that in situ at Gale that should constrain the CO2. Perhaps we can talk more.
Yes, thank you. Let's talk later.
Again? Okay, and then finally we have the last talk of this session, which will be by Arihiro Kamada, excuse me, who will be talking about simulating formaldehyde production and fluvial transport on early Mars using a global climate and river model.
So I'm Arihiro Kamada. So this is the second time for me today to give a presentation. So in this time, I will talk about the formaldehyde production in the atmosphere and fluvial transport of formaldehyde to the Martian ocean on early Mars. So this is the same slide in. So early Mars would be warm and wet climate. So as you know, previous GCM models such as LMD and Japanese group and other group can succeed to reproduce the warm and wet early Martian environment with a hydrogen-rich atmosphere. So they reproduce a stable existence of surface liquid water. So however, the presence of organic matter and as a life precursor molecule environment has not been well studied in the GCM studies. So according to the Koyama and Kamada last year's paper, so a large quantity of formaldehyde may have formed through photochemical reaction in the atmosphere. And this this created formaldehyde dissolved into raindrop and fall into the Martian ocean. And this yes. And this formaldehyde in the oceans or lakes so can change to the sugars, and finally change to ribose, which is the main building blocks of RNA. So it is very important to origin of life. So the organic matter so rarely exists on Mars. So indeed, the curiosity rover recently detected so bulk a lot of amount of organic carbon in sedimentary rocks at Gale crater, so which suggested that so the 3.5 gigayears ago, so Gale crater would be a habitable rock stream environment in the Mars. So in this study, we estimate the amount of organic produced in the atmosphere and deposited amount in the Martian ocean and lakes. And we estimate the transport of organics by rivers, organics and sediment by rivers to the ocean and lakes. And in this study, we used the Japanese Miroku model, three-dimensional GCM, and in this study, so we assumed the 2-bar CO2 H2O mixing atmosphere with hydrogen, 6% hydrogen gases. And in our simulations for the production of formaldehyde in the atmosphere, using the lookup table diagnosed by atmospheric temperature, pressure, water vapor amount, and UV flux in the atmosphere. And then this produced formaldehyde dissolved into rainfall or absorbed by the snowflakes, and they fall into the Martian ocean and lakes. And then we calculate this dissolved formaldehyde into the groundwater and upwelling water, and this river flow of water and formaldehyde into the ocean and the lakes. And so we used the same topography of the before the true polar wonder with the sea level below minus 2.3 kilometer. And this is a simple result of our study. So left figure shows the atmospheric temperature and atmospheric pressure at water column density and UV flux at the top of atmosphere. And then in this case, our model produced a warm early mass with a surface temperature of 218 Kelvin. And our model produced a water-rich environment on the ocean and near the shoreline region on the lake. And this, using the lookup table in our study, so we can diagnose the atmospheric formaldehyde humidity, so right figures. So the formaldehyde density is very proportional to the H2O column density. And if the H2O column density is same value, so in the low latitude where the UV flux is stronger, so H2CO, more H2CO reproduced in the atmosphere in your model. So this is the rainfall and snowfall in our simulation. In this case, in this study, we assume the 6% hydrogen case, so we reproduce the warm early mass. So most of the precipitation is formed of rainfall. And in our study, so most of precipitation occurs in the ocean and lakes and seashore regions, and rainfall value, annual rainfall is 150 millimeter, and snowfall is just only 4 millimeter in mass year. And this is a total of 190 millimeter per mass year. The next figure shows a formaldehyde fall by snowflake. In our study, so the surface deposition of formaldehyde was 380 million kilograms by rain droplets and only 64,000 kilograms by snowflakes. So this figure shows the annual sediment flux, and the left figure's capture is wrong. Left figure's caption is the annual formaldehyde discharge. So as shown in right figure, so the annual sediment flux to the Martian Ocean is annual transport of sediment to the Northern Ocean is 450 million cubic meter and 76 million cubic meter to Hell spacing in annual. And then, so annual H2CO transport to the Northern Ocean is 85 million kilogram and only 2 million kilogram to Hell spacing. And if this situation continues, so these formaldehyde transport environment may have promote the formation of complex organic compounds in the Martian Ocean and lakes. And so, assuming the formaldehyde and sediment were deposited in layers in estuaries of the Martian oceans and lakes, so we can estimate the organic carbon in the sediment rocks in the Mars. For example, so in the Northern Ocean shoreline, so we can estimate the organic carbon is 37 micrometer carbon per gram in the sediment, and near the Hell spacing, we can estimate the value of 5.3 microgram carbon per gram. So, given there, by the observation of Curiosity rover, so they observed the 200 microgram carbon per gram organic carbon in the sediment near the Yellowknife Bay lacustrine mudstones. So our model, 38 microgram carbon per gram. So some of organic carbon can be attributed to atmospheric produced H2CO in our model. So in future work, in the next step, we will simulate the H2CO accumulation in each early Martian crater, including Gale crater, at more higher resolution. Thank you.
Thank you. We've got time for quite a few questions, I think. So, anyone? All right then. Well, let's thank all our speakers again. And, yeah, so I guess coffee should be ready in about 5 minutes. So yeah, thank you.
Yeah, I plan to work with JB. What I'm about to say has nothing to do with what I'm doing at LMD, but you have 13 minutes. Yeah. I might. There is a timer.
They know because it becomes orange.
Okay, let's get going with our last session today. There's still one more presentation in the early Mars climate modeling session, and that'll be by Connor Metz and colleagues, talking about sulfur's decisive role in driving early Mars climate evolution. Take it away.
All right. Hi, everyone. I'm Connor. I'm a graduate student at University of Michigan, and today I'm going to talk about my work on sulfur on early Mars. So the question I wanted to answer is, what caused the Noachian-Hesperian transition? We know that Mars had at least an episodically warm climate with fluvial activity, and then we see a strong climate transition occurring at the Noachian-Hesperian boundary, and the climate becomes dry with a lot of sulfur and possibly cools off. So what caused this climate change is what I wanted to investigate. So this is a figure from Parsons et al. 2025 showing the volcanic floodplains from the all across Mars, and you can see that most of them date to the Hesperian period, around 3.5, 3.1 billion years ago. And what Parsons et al. Did was calculate how much sulfur could have been released to the atmosphere by modeling the amount of sulfur in the magma, and then subtracting off how much sulfur there was in the crust after it would have cooled. So they get a really huge number of 6 times 10 to the 17th kilograms as an upper limit, how much could have been released during the whole Hesperian. And for reference, if that was all in the atmosphere in the form of SO2, it would be like 300 millibars at the surface pressure or 175 millibars if it was H2S. So that's quite a lot of stuff to be putting into the atmosphere. And so what kind of climate impacts would this have had? Well, that answer to that depends on what redox form you assume that the sulfur builds up in the atmosphere. And that depends on the assumptions that you make about the magma plume's behavior and its composition. So if there was an oxidizing atmosphere with a lot of water in there, the sulfur would be converted to SO, and SO2 would build up. And if it was a very reducing atmosphere with hydrogen, then H2S would build up. And so I take these as two end-member cases, supposing that all the sulfur emissions were SO2 and all the sulfur emissions were H2S in other cases. So both of these guys are greenhouse gases, and they would ordinarily warm the planetary surface. But as has been shown before in the literature, they decompose photochemically to form S8 and H2SO4, which form aerosols, which are very reflective, causing a net cooling to the planetary surface. And so this is how it works. Stuff is injected, it photochemically forms this, and the aerosols, if they're small, they're very reflective, and not much light gets through the planetary surface, which causes a cooling. And if the aerosols are large, then they're forward scattering, and they can warm up the planet, and these guys act like greenhouse gases. And so the aerosols will deposit on the surface, leaving behind their sulfur. And so it seems to be preferred in the literature that the small aerosols are the more likely case from looking at Venus and other places. So probably be a cooling, but I leave this as a free parameter in my work. So could it have been this sulfur-induced cooling that caused the Noachian-Hesperian transition? So if we even had an episodically warm and wet Noachian, this kind of cooling would like depress the global temperatures, and so you'd get less fluvial activity in the rock record and a sort of drier Hesperian. Because it's so cold, basically all the water would freeze, and then what would happen is the sulfur would deposit out onto the surface, which maybe could leave behind all these sulfate units that we see all across Mars. And this has been a hypothesis proposed in the literature before by Laura Kerber and other people, but this is what I wanted to test. And so for methods, what I did was developed a 1D climate evolution model. I run a large grid of cases, like 1,000 cases with various composition, evolve them for 100 years. I start them all from warm Noachian climates with CO2 and water in the atmosphere, and then half of the grid has enough hydrogen to get them above freezing from the hydrogen CO2 CIA. And so I test a large range of sulfur emission rates as my big free parameter. Where I get these emission rates is supposing you have this total amount of sulfur that was released over the whole Hesperian. If you assume it was released over 1 billion years, you get this very slow drizzle sort of emission rate. And if you assume that all of the sulfur was released over 10 years, then you get this very fast emission rate. And I test everything in between these two end-member cases. And so you can link basically any sulfur abundance that you assume is emitted in one event, you can link that to a timescale. And so even if you had half the total sulfur emitted in one event, you can figure out a timescale for that emission, assume a timescale rather, and figure out what sort of flux would have been emitted, and figure out what kind of climate this would have had. And then I test a whole load of other free parameters, and I see how the climate evolves. And so this is my model. I give it a funny name. It's a radiative convective model in 1D. Basically, it's just a coupled photochemical model and a radiative transfer model. The photochemical model comes from Nick Wogan. It's in the Atmos family of models, and it handles the composition and condensation in my cases. And then the radiative transfer model comes from my advisor and myself at Michigan. We do correlated K, and this handles the temperature evolution in the atmosphere. And we solve this system in real time, so we can get non-equilibrium evolution solutions. And we've validated a model with other early Mars published work. So in general, looking at some general results, sulfur aerosols control the climate. We do get cooling even at the lowest sulfur fluxes. So looking at this green line here, it's a very low flux. The H2SO4 is building up in the atmosphere very slowly and causing it to cool off. The larger fluxes, like this orange line here, you can see the cooling occurs very rapidly, and we get cooling by tens of Kelvin over a short period of time. And then we do get a warming when the aerosols are large. So I did some sort of back-of-the-envelope calculations on how long this cooling could last. I haven't done anything fancy about the lifetimes, but just sort of so far, this is how I've calculated some lifetimes. So the SO2 cooling or warming can last at least a few million years, I guess. I can't really run my model for millions of years, but what I've done so far is just, you can assume all the sulfur is converted into S8 or H2SO4, and then I divide out by the deposition rate of these things out of the atmosphere. And I take the maximum deposition rate at any of my cases, and so this gives me a lower bound, and the number that I get is 25 million years. So cutting that by an order of magnitude, I figure conservatively could last at least a few million years. The hydrogen sulfide cases last less time because the S8 deposits out faster in these cases for thermodynamical reasons. So that's the general results. I got some really interesting results from looking at stronger eruptions. So all of these are pretty strong eruptions, but for example, looking at Hesperia plenum, that accounts for about half the sulfur that's released over the Hesperian alone. And if we look at the timescales of large igneous provinces on Earth, they all erupt in less than about 1 million years. And so you can infer by analogy that all of these volcanic eruptions are pretty strong. So what happens if you emit purely hydrogen sulfide is that the atmosphere ends up collapsing. And so at fluxes greater than these here, you start hitting a threshold at which you form a lot of S8 in the atmosphere, which is very potent cooling. And so if you assume this kind of timescale of eruption of sulfur, you get this kind of fluxes, and this is consistent with the eruptive timescales of large igneous provinces. Whoops. So basically how it works is the S8 starts building up in the atmosphere, the surface temperature drops until we hit the CO2 condensation point, and then the atmospheric mass drops because CO2 is condensing out. And so collapses happen pretty quickly in my model within about 1 to 10 years. And they could be permanent, or they could be more temporary, and the CO2 ice would sublimate back and the pressure would come back. So we know that the modern Mars atmosphere is thin, but did it thin out gradually over billions of years, or did some kind of collapse like this really occur? Well, it would leave behind signs in the rock record, such as very cold surface temperatures and pretty much no water activity whatsoever on the surface during this time. The precipitation rates are pretty much nothing. And these high hydrogen sulfide fluxes leave behind other traces in the rock record. They have very large S8 to sulfate deposition ratios exceeding 10 to 1, which is very weird. Usually it's sulfuric acid dominated. So what we can do, I propose, is you can observe the native sulfur to sulfate ratio on Mars, and assuming a volcanic episode, you can kind of back diagnose the sulfur injection magnitudes and the atmospheric redox state. So another really weird result that I get is that if you assume SO2 emissions, the SO2 can actually rain out as a liquid at high fluxes. So the SO2 destruction rate ends up leveling out as a function of injection rate. And so it approaches this constant. When you have fluxes greater than 10 to the 11th molecules per centimeter squared per second, the SO2 can build up in the atmosphere. And so you need about 50 millibars for the SO2 to rain out, which is about 1/6 of the total sulfur released over the whole Hesperian. So Hesperia planum could probably cover that amount, and then you need the temperatures of around 200 to 260 Kelvin for this thing to be in a liquid. And if you emit this large amount of sulfur over the large igneous province timescale, this does work. And you get precipitation rates that are pretty much roughly Earth-like. This is 1D, so it's global and temporal average. And as far as lifetimes for this, back in the envelope, I get an answer that it could probably last for a couple million years. Don't pay too much attention to these spikes here. I think they're just some numerical weirdness, but I do trust this kind of continuous background rate. And so can this SO2 rain scenario explain some of the post-Noachian erosional features that we see that are not co-eval with phyllosilicates or other hydrates? And so I think this sort of hypothesis could provide us with a simpler narrative for Mars' climate history. We don't need warming and cooling episodes. Instead, what we could have is just a warm episode in the Noachian, and then it cools off with the Noachian-Hesperian transition, and then we have SO2 doing this kind of erosion, if it can even erode rock at all. So maybe if there is some hydrates in the atmosphere, maybe they came around afterwards. I'm not so sure. So in conclusion here, just kind of summarizing this, I think sulfur can work to cool off the planet and potentially explain the Noachian-Hesperian transition, turning Mars into a frozen desert that it is today. I think it could also work to explain all the sulfur that we see on the surface of Mars today. And my sort of other weird scenarios may help to explain other mysterious aspects of Mars's past climate. And I hope that in future work, we can rigorously test which one of these scenarios, if any of them, are compatible with the rock record. And that's all I have. Thank you.
Thank you, Connor. This paper is open for questions. Come down to the microphone, please. Yes, go ahead, William.
Hey Connor, I'm William, CNRS Europe. Great talk, thank you. I think we need to get in details about how the volcanoes affected the early climate of Mars, so that's great work you're doing. In the eruption, the modality of eruption, did you consider effusive or explosive eruption? What's the time frame and the time scales of the release of gas in your model? I didn't catch it.
Yeah, it's a constant release into the atmosphere, and so what I did is basically, to get these initial rates, what I did is you can assume this is the total amount of sulfur that was released over the whole Hesperian, and then basically I get these different rates. And this one comes from a lower, if you assume that all the sulfur was released over 1 billion years, you get this lower bound of a slow rate. And if you assume it was all released over 10 years, you get this upper bound. And then I test everything in between, and you can link different sulfur amount eruptions to timescales.
Okay, so if we instead investigate bursts, so explosive eruption or different style, that's still a model that we need to put on top, right? With more extreme.
Yeah, that would be cool to check that out.
Okay, thanks.
Yeah, thank you.
Hello. Very interesting talk. Erwin Kite, University of Chicago and Astera Institute. For the collapse timescales, the latent heat released by the CO2 will make it harder to condense subsequent CO2. So there's a kind of speed limit of about 1 millibar per year. For the aerosol lifetime, maybe I didn't catch it. The lifetime of the individual aerosols will be a few years at most, because if it's too small to gravitationally settle, then it'll be so light that it will be lost by Brownian diffusion when the wind brings it close to the surface. But I'm not sure. When you referred to 2 million years of cooling, were you thinking about aerosol-induced cooling, or were you thinking something else?
Well, I did it's just back of the envelope calculation of aerosol cooling. Yeah, I'm not sure that I'm following exactly what you're saying, but I'd love to talk afterwards with you if you wouldn't mind.
Hi, Ashwin Browder from the Astera Institute. I was just kind of curious, how have you initialized the kind of the water vapor content in your atmosphere? So how humid is your atmosphere? Because I would have thought, you know, first of all, the SO2 is going to react with water in the atmosphere to form H2SO4. And then also with the SO2 rain, it's also, the SO2 is also going to dissolve in the droplets. And the SO2 could also dissolve, actually, it could be adsorbed into the regolith. But yes, I was just curious, first of all, how you initialized your water cycle in the atmosphere, how you parameterized that. Thank you.
Yeah, initially, when the atmosphere is warm, it's pretty much at saturation, and then it quickly cools off, and so it sort of condenses out and follows the saturation vapor pressure as it cools off.
SO2 rain even with that?
Well, it's, yeah, a lot later, like years later this happens, like after the cooling.
Wow.
Yeah.
Thank you.
Other questions? Just, I'll just ask one, just to be clear, the sulfur particles are the only aerosols in your model atmosphere. No dust, no other water clouds, CO2 clouds, nothing, just sulfur?
Yeah, not radiatively active. We had CO2 and water and other stuff condensing out, but the only radioactive aerosols was the S8 and the H2SO4.
So, I mean, dust is a radioactive aerosol. You might want to play with adding in some typical dust abundances.
Yeah.
Okay, other questions? If not, let's thank our speaker again. Thank you. Okay, that concludes the early Mars climate modeling session, which was really cool. Now we go to the early Mars environment session, new inputs from mineralogy and sedimentology. And the first part of this will be 3 fun talks on lessons from curiosity and perseverance. And Kathy Quantum-Nataf will be our first speaker. Take it away.
Thank you. Okay, so I'm going to try to give you a review of what we learned so far with Perseverance on the rocks that are older than 3.8 billion years, so it's very ancient Mars. But first of all, I will take a little time to remind you what is the geological context of Perseverance, because it has strong implications when we want to interpret what we have in situ. So Perseverance landed in Jezero crater, that year on the margin of a very big impact, Isidis giant impact, and investigate these complex geological cross-sections. I'm going to try to explain you very quickly. So Jezero is out here, on the margin of Isidis impact. Isidis impact is large enough to have samples and excavated mantle, lower crust, and upper crust, and made a thick ejecta of these ballistic materials. And actually, it is what we are observing in the regions around Isidis impact. We are observing this very disturbed Noachian basement, partly made of mega blocks of different size and different tones, and deformed layers. So a very complex basement, strongly affected by Isidis impact. Here, this is just in gray, the distributions of the mega blocks attributed to Isidis impact, and some of them are exposed in Jezero craters. Then Jezero emplaced on this very disturbed Noachian basement and get eroded. How do we know that? We know that from the topography of Jezero, that is an eroded impact craters when we compare Jezero crater to a crater of similar size, about 50 kilometers wide. There is just one Arc Graves that is just next to Jezero, that is a fresh impact crater. So the depth is way more depth in fresh craters than in Jezero, and the crater rim also has been highly eroded in Jezero compared to a fresh impact craters. And at some points, this Jezero crater has been a paleo lake, and Nicola will probably talk more about this. So after a disturbed Noachian basement, we have the formation and the erosions of Jezero crater. Then we have a regional olivine carbonate-bearing unit. We know that from orbit, that is very widespread in the regions over thousands of kilometers, square kilometers, that is enriched in olivine and more locally in carbonate. And Bethany spent a lot of time working on this carbonate. What is interesting is this unit is large enough to have been dated by crater count and push the formations of this unit or exposition of this unit older than 3.9 billion years, which means that J0 is older than this unit because J0 craters and its completely eroded northern rim is draped by this regional olivine rich unit. Okay. And then, capping this olivine-rich unit, there is a mafic cap, and that is on the top of this mafic cap that we have fluvial and lacustrine deposits that we are observing in J0 at the outlet of Neret Favalis. And Nicolas will talk about this fluvial deposits. So Perseverance landed here on the floor of J0 craters about 4.5 years ago, studied this capping unit, the olivine carbonate-rich unit on the floor, then climbed the delta fan, and studied also, you will see, the olivine-rich unit here on the margin of J0 craters. And since a year and a half, we are studying the crater rim of J0, where the Noachian basement is exposed. So it's a large pile of rocks, and a large span also lapse of time between early Noachian rocks to late Noachian, early Hesperian rocks we have encountered. And I'm going to talk about this, what we learn on olivine carbonate-rich unit and what we learn on this very complex Noachian basement. So, just an aside, Perseverance is a complex machine, but a lot of the results I will show you are coming from SuperCam instrument that is doing a remote analysis of rock compositions, doing different methods. We have elemental compositions, and we do have mineralogy from passive Visayar spectroscopy and Raman spectroscopy. Okay. So what did we learn on the regional olivine carbonate unit? So we visited this unit twice. First part at the beginning of the missions on the crater floor. Here on this map, you do see in color, it's from orbital data, you have in red olivine signatures. And this is the main component of the crater floor, but also the component of the unit we call margin unit that is on the border inner border of J0 craters. And there is a difference from orbital data between the crater floor, that is mainly olivine, and the margin unit, where in this map, this is a paper from Bryony and collaborator, that on the margin part, we have a strong carbonate and alteration signature. So that's what we knew before landing. And what we learned is that these rocks are made of millimetric grain of olivine, a lot of grain of olivine. And to make this kind of rocks, we need an accumulation, sort of magma chamber, of an igneous process to accumulate olivine grain, millimetric grain of olivine. We detect olivine with all instruments, including Raman, spectroscopy from SuperCam. And what is interesting also is that this unit in different parts may also be highly altered, and with two members of alteration. Here in this diagram, you have here iron, magnesium, silicon, and CNAK, and you have here olivine compositions, and it is going toward two trends. One here that is iron magnesium carbonate, a carbonate that the detections are confirmed on Raman data in all the unit, from the floor to the margin unit, but with a higher content in the margin unit. And the second end member is this silicon-rich, let's say, point minerals we interpret as a hydrated silicate as a product of alterations between the carbonations. Here are the Visayar results, where we do confirm strong olivine signatures, this very wide one micron absorption band, but it's also combined with a complex alteration combo. First of all, we have a pair absorption at 2.3, 2.5, that's carbonate, but we have a stronger 2.3 bands, which means that we have iron magnesium phyllosilicate. But we also have a 2.2 absorption band. We know from combined analysis that it is due to SiOH bond. So we have here a presence of olivine-rich unit with mixture of carbonate, phyllosilicate, and hydrated silicate. We know from other instruments within the rover that it's probably low temperature alterations. It's quite pervasive. Huh? It's not like veins of carbonate. No, we have a pervasive alterations. We wonder if there is a role of the Jezero Paleo lake or not in the alterations of this carbonate. For instance, in the margin unit, we have higher content of carbonate, while on the floor it's more reduced. So maybe on the crater floor we had sedimentary protection from interaction between the water lake and the rock. These widespread carbonate detections have consequences, let's say, implications for the carbon storage within the Martian crust. So doing a very conservative calculations that we have in these rocks from 10 to 20% of carbonate. If we are using this value, 10%, very conservative, on the widespread olivine-rich unit we have in these regions, we may have a store of the order of 2% of the current mass of the atmosphere, carbon mass of the atmosphere. But if we are doing like less conservative calculations, if we are extrapolating, for instance, the carbonate content here to all olivine detection on Mars, because we have seen in Jezero that the carbonation is strongly linked to olivine-rich rocks. So if we are extrapolating this to all olivine detection on Mars, we may explain like 1 bar of CO2. That's very speculative, but I mean, carbonations is we have the proof that carbonations is an efficient way to store carbon in the geological record. Now I'm going to switch to this very complex Noachian basement we have been studying since we climb the crater rim, actually, since last year. So, and we arrived at the summit for last year Christmas. It was a nice Christmas present. Yeah. And in this crater rim, what is exposed? This is this complex Noachian basement that has been uplifted in the crater rampart. So it's quite well exposed in the crater rim. The ascent is about 400 meters. It wasn't easy. We had to do some zigzag to complete the ascent, but we made it. And here, this is a sort of an overview of the traverse we did. So the first was the inner rim ascent. In this inner rim, we didn't have so much exposure, actually. As you can see, there is a lot of regolith. So we saw a lot of float rocks. It was hard to really see the context, let's say, but we have a lot of structure here that have the same direction as the crater rim. We suspect there is some fault system related to Jezero crater. So we suspect that here we are in the inner terrace of Jezero craters. And we mainly see a lot of exposure and easy to, let's say, understand in their context on the outer rim of Jezero. And anyway, on this entire traverse, we saw a lot of geological diversity. We saw plagioclase-rich rocks, basaltic rocks, pyroxene, rocks that were highly altered, some other non-altered at all, so a very large diversity. And we collect 5 samples, mainly on the outer part of the crater rim, so 5 samples. I will not talk a lot about the inner rim because like I said, the context is not that clear. But just one thing here, this is just a collection of spectra within this inner rim that illustrates the spectral diversity we have there. We do have like pyroxene, signatures of sort of perfect pyroxene. What is important is to see that you don't have 1.9 absorption band that is related to the water, which means that it is a non-altered rock. And in comparison, we have a lot of rocks that have strong alterations with sulfate signatures, iron magnesium phyllosilicate signatures, aluminium phyllosilicates, so a large compound of different alterations. And also, what we saw here is the first detection of quartz on Mars, and Olivier Bessac will talk about this more. But what was interesting is that we saw in float rocks, but float rocks align in the same directions as the crater rim, so probably linked with the fault system related to J0 impact craters. And there we saw rocks almost made entirely by quartz, and with a Raman detection perfectly fitting a hydrothermal quartz crystal. So we think we have evidence of a J0 impact-related hydrothermal system. Then, after reaching the top of the crater rim, we went down and we saw a nice cross-section. The upper part of the rim is made of mega blocks, you will see. And we collect 2 of these mega blocks in samples. Then we do have about 100 meters of a layered sequence. We have layers that are deformed, fractured. It's a long story. And at the base, we transitioned to this unit in high-res image here that is different in color than the layers, and that has also a different compositions. So let's start with the upper part. So in the upper part of the crater rim, we do have a lot of mega blocks we can see on orbital data. And we went to a location called Shallow Bay, where we do have 3 blocks of different color, 1 pink, 1 blue, and 1 yellow. And these blocks are the size of about 4 by 8 meters, and with a diamond shape. And when we look at their spectral signature, it's very different. The blue block here has a spectra of a low calcium pyroxene, non-altered. The block number 2 has a spectra in agreement with iron and magnesium phyllosilicates. And the block number 3 has a very distinctive spectra fitting perfectly a magnesium serpentine with all the absorption features we have in a lab of like pure serpentine. And if we look at the LIPS data of this serpentine-bearing megablock, all the points are above the olivine standards that are lying within the magnesium serpentine standard. We do not see any olivine minerals or pyroxene, so we have no relic of precursor minerals from Supercam or other instruments. In Raman data, we saw for the first time the OH stretching band for the first time in the missions, which makes sense because it's a lot of water within the magnesium serpentines. But something to note, it is we have a few iron in the bulk rocks, in the rocks, that is enough in the protolith to have produced hydrogen. And also a fun fact here, this is a spectral soap in the visible domain. It means that it is the redness color of Mars, all the points, except this block that is green, let's say. So we have evidence here because we have 2 mega blocks, this blue one up here that is absolutely not altered, and this one that is entirely serpentinized. We have 2 blocks next to each other that have been put together and not modified since then, which means that the alteration dates before the giant impact that made these mega blocks bearing unit. That's what is represented here. We have like a pre-Isidis crust with some parts that are entirely serpentinized, either the lower crust or the upper mantle. Then we have a giant impact, very likely Isidis, that creates a mega blocks bearing unit with blocks of different parts, part highly altered, part weakly altered. And then J0 form within this mega blocks bearing unit eroded, and now we have exposed this mega blocks bearing unit. So, and we have now in J0 the evidence of intense serpentinization process. It's probably in the subsurface because we don't see widespread serpentine detection on orbital data. in the Noachian basement. But it has a lot of implications on the water storage within the Martian crust, because serpentine, it's about 13% of rocks, 30% of water that are in serpentines, which means for these blocks of rocks 4 meters by 8 meters, we may have stored up to 10 tons of water just in this block. So it's maybe a very efficient way to have stored water in the subsurface through Martian history. And we suspect with this serpentinization the productions of H2 and possibly global warming. And I will not discuss the implications for life emergence in serpentine's context. Here I have 2 slides about the layers and what we have below these megablocks bearing units. But something you have to keep in mind, this is very recent data, so that's our best summary, but we still have to digest all this data. But we see also a 6 seconds of layers. So these layers sometimes are fine grains, sometimes coarser grains, but whatever, they have a very strong average basaltic compositions. And surprisingly, we have very weak alteration signatures. So that was surprising for Noachian layers. We interpret these layers to be possibly aerial deposits, either volcanic or impact related, because we have located within the layers sometimes some spherules we think are atmospheric related processes. And for the atmosphericists who are in this room, we do have 1 sample with this kind of spherules that may have trapped the ancient Martian atmosphere. And then below these unaltered basaltic layers, we are transitioning into the base of the sequence that has the similar basaltic compositions, but a very different, that's my last slide, that are similar basaltic compositions in lips, but a very different signatures in Visaya. We have a strong phyllosilicate signatures. And what is interesting is that these phyllosilicate signatures, if you are an infrared spectroscopist on Mars, this is exactly the main type of signatures we have elsewhere on Mars in Noachian terrain. This is what we observe most of the time, this kind of signature. So it's maybe the signatures of the alterations of the basaltic crust in the Noachian time. So here is my last slide. In conclusions, what we have learned is that in early Noachian, mid-Noachian, and even pre-Noachian, because these megablocks are telling us something older than the surface age of Mars, so that we had various environments with low alterations or high alterations, whether it is from difference between surface and subsurface or intermittent water-related processes. So we have evidence for intense subsurface serpentinizations, weakly basaltic layer alterations, phyllosilicate unit, so that probably alteration product of this basaltic layer, and non-altered pyroxene. We also have in mid-Noachian, right after J0 formations, evidence for hydrothermal cells. So we had water in the system by that time. A lot of erosion also of J0 impact craters. And we have in this olivine-rich unit evidence of carbonations, which has consequences for carbon sequestrations. And then I will just transition with the next talk from Nicolas that will tell you more about the early Hesperian, Noachian early Hesperian history of J0.
Thank you, Kathy. This talk is now open for questions, please.
Adam Valentinos, ETH Zurich, formerly Brown University. Nice work. I would like to ask you about the serpentinization you mentioned in the rim. So we have a paper now in GRL and Review where we employed ICL2D simulations, and basically we're seeing that the rocks in the rim, they experience low shock conditions, so low pressures and low temperatures. So basically it kind of suggests that the rocks in the rim are the pre-impact target surface materials that were not shocked that much and not altered and changed. So it just basically suggests that it's, you know, you're having a cross section through the pre-J0 impact crust, and you're depositing materials in the rim. So does that agree with your interpretation, or not so much?
No, for sure, what is a crater rim? This is pre-J0 rocks. But these mega blocks are probably even pre-big impact. Does that make sense? Yeah.
So the serpentinization was taking place before the impact, you're saying?
Yeah.
Not in situ, okay.
Yeah. We really suspect this mega blocks bearing unit that is exposed in J0 to be related to the regional mega blocks bearing unit around Isidis that is possibly likely from Isidis impact. So yes, that puts the serpentinization before Isidis impact. So very early. And that's why I'm saying it's probably even pre-Noachian, because early Noachian is defined by a crater retaining statistics. And so the early Noachian, this is units that are exposed actually on the surface. And this serpentine is probably something that is buried. So we may see pre-Noachian rocks.
Okay, any others? No. Oh, Bethany, yes. Go ahead.
Thanks, Kathy. I wanted to just ask on the carbon sequestration angle, the one comment that you made about olivine units and holding, potentially holding more carbonate than we see from orbit. Do you feel like we now have a good database based on the rover data of, for every given sample measured with VisIR, kind of a sense of what the detection limit is for how much carbonate it takes to be seen in the orbital data? Because of course, this is a unique site in terms of the olivine units, in terms of it's one of only maybe, I don't know, half dozen where carbonate is actually seen from orbit.
No, you're probably right. I don't know if we can really extrapolate to all the olivine-rich unit on Mars. It was to have like a range of the possible. But I prefer what is the conservative way, what may have been stored in the regional unit, and so that's only 2% of the carbon budget of the current atmosphere. And about the link between what we are seeing in VisIR, the main difference between orbital analysis and in situ analysis is probably the mixture with the regolith that is not altered, more than really that, because we are seeing very like a few percent of the rocks sometimes. Carbonate, it's 10% of the rocks, and we saw that very well in the orbital data. So it's more that we are underestimating this alteration product because of the mixture of unaltered regolith.
Related to that, where I know the olivine unit is a bit enigmatic in a way, but where would it be in that time frame? Would be in the late Noachian, the
olivine unit
that is a bit carbonated.
No, it is in the late Noachian.
Late Noachian.
Yeah.
Sometimes shortly after J0.
It is draping J0 North Rim. Yeah.
Okay. Any more? My only other question is, when are those samples coming back to Earth?
You want the composition of the ancient atmosphere.
Thank you, Kathy. Let's have a hand for our speaker again. Thank you. Okay, continuing on our rover adventure, Nicolas Mangold and colleagues will answer the question, what do the fluvial lacustrine sedimentary records at Gale and Jezero craters tell us about the past climate of Mars? Get away.
Thank you, Jim. And I will run directly into the image here. Oh, yes, okay. So I will touch only the sedimentary fan of Jezero in this talk, and Cassie already introduced well Jezero, so I don't need to come back to that. I'll pass directly to one of the key observations we had in the first part of the mission, which was from remote, from 2 kilometers away. We had this wonderful cross-section where we saw in this part subhorizontal layering with cross-bedding interpreted as fluvial beds, and in this part steeply dipping beds over 20 meters high sequence with sigmoidal geometry, which is typical of what we have on Earth when we have lake deposits just fluvial beds going into the lakes with faucets. What we call faucets are the most steeply dipping beds in this case. So this is typical of the architecture of a Gilbert Delta, where Gilbert just means that we have rivers, fluvial beds entering directly into a deep paleo lake, at least 20 meters in that location. Something of interest also is that the lake level here is 100 meters below the bridge, which is to the east. So whether Jezero was open lake system once, perhaps, but at the time of formation of this material, it was a closed lake system. And we'll come back to that in a few seconds. So now after with the rover, we explored several places in the front of the delta, and one of the key places we observed this soft material, very recessive to erosion, so very weak to erosion, very different from the hard material which forms the faucets of the delta here. And this material, what we take a look with the abrasion, when all the instruments, it's clearly very small grain, siltstone or mudstone, which typically form when you have very, very quiet deposition and environment, so in a lake bed, and this corresponds to a lake bed and or distal bottom set from the same deltaic deposits. So we took 2 samples here because, of course, they are very interesting, and I will come back to the key mystery of this material just a little bit later. So now around the fan, we have made several observations with remote cameras, ZCam and Mastcam Z and SuperCam RMI, about different locations where we observe the same geometry as in Kodiak. For instance, here we have steeply dipping beds with horizontal beds at the top here, so same sequence, fluvial deposits with the entrance into the lake. In this location, we have the horizontal top sets, so fluvial beds, with the faucets being in a different geometry. It's just because here the section is frontal, so you see the beds dipping in front of you. And typically it's always 25, 30 degrees, which is what we wait for a gravity current-led depositional styles that you have in this kind of faucets. And this one here is also interesting because you have 20 meters 6 seconds of faucets which lie at the top of the fan here. So the elevation of these different transition from top set to faucets is at different elevation. The position is at different elevation all along the place. And when we pinpoint all the elevation we find with the top set faucet transition across the sedimentary fan is what we find. And we have an overall decrease of the elevation from minus 2410 to minus 25, so almost 100 meters of elevation of the change of the lake level, which makes that the lake, the delta is actually a step delta, a downstepping, which is due to the progressive lake level fall, which is called forced regression in a sedimentary environment on Earth. And this is an overall progression of the lake and decrease of the lake level in the past. And also what you can notice is that even at the uppermost elevation here, this is still just 10 meters below the bridge of the delta of the Jezero crater to the east. So we found most of this in a closed lake system. The bridge is here. And actually in another work, we show that the outlet valley is actually probably just overflow valley with several sporadic overflows which form these valleys, and most of the delta found below the elevation of the bridge, which means that, okay, it was maybe an open system once, but perhaps short-lived, and then was a closed system while it was forming the delta. And this has importance on the water chemistry because you can have easy evaporation when you are in the conditions of a closed system more than in an open system. Going to the fluvial activity, so in some places we were able to touch the top set, but the fluvial beds at the top. I will just discuss this one shortly because it's a key one. It's a place where we have the top set faucet transition. These are faucet dipping toward us. And this is a typical section that we can draw from the delta front with the fluvial beds here, the deltaic faucets and the bottom sets. And this is a fluvial bed that we can see here, very, very close up from the SuperCam RMI here. You can see the scale, 1.5 meters for the length of this boulder. And you can see these different boulders are imbricated and rounded, and they show what we call a fining upward bed, which is typical of what you can wait for a fluvial sedimentation along a kind of fluvial bars along lateral accretion. So here we are able to estimate the discharge rate, which are of several hundreds of cubic meter per second. And we also say that it's probably very variable fluvial activity, fluvial regime in this location, because just above and nearby you have also sandstone or conglomerates with much smaller pebbles than in this case, so we probably have strong variability in the fluvial regime. So going now to the composition in a few slides, the bottom set beds, which are here, are dominated by both phyllosilicates and sulfates. And the first set beds, which are here, dominated by carbonates and olivine, which they have a very similar composition to the marginite. Probably not a coincidence. Probably the source of this material is taken from the olivine-rich unit, which is upstream. And the second plot here, so this was the supercam Visayer instrument and this part of the lips. But it's not the bulk chemistry here. In the paper by Elise Clavier, she took the location, the points with the supercam lips that fit the most the stoichiometry of some minerals, and what we found the most are olivine, carbonate, and ice silica. And this assemblage is similar to what Cassie showed you in the margin unit, in the olivine-rich unit, which is above us and older than us. So either we have the same type of alteration with a carbonatation, or the reworking of the olivine-rich unit, which is rich in olivine and carbonates, which is reworked in the delta later. But what is important is that we have the preservation of some part of the olivine, and this is significant in terms of alteration, because on Earth, usually olivine is very quickly altered, and it is preserved, for instance, in Iceland when temperatures are cold and the material is young. And so you need either to have low temperature or limited duration of activity to preserve olivine in such kind of environment in a lake. So the overall idea for J0 is that the duration of activity must be relatively short from what we observed. And the duration has been debated for a while with very different numbers from 10 to 10 million years, basically. Much different difference, and I will invite you to go to the poster by Justine Villette, who is somewhere over there, tomorrow to discuss this model, because we find a duration of several thousand years for the formation of the J0 delta with the different assumptions that we have done here, including the fact that we are probably in a kind of cold environment with either snow melt or glacial melt producing the river streams that we see the beds downstream with the lakes. Okay, so that was J0. And now moving to Gale crater, this is a much different environment because we have a much thicker part of sedimentary layers. Look at the Mount Sharp. Most of it corresponds to sediments, and I will limit myself to the clay unit, which has been defined from orbit as a clay unit, which is now called the Murray Formation from the ground. And William Rapin in the next talk will detail everything corresponding to the transition from clay to sulfate and where we stand now with the rover. This is well known. It's the first big place we traversed with curiosity at Gale crater. These mudstones are very interesting for many reasons. They find the finding of organics in this material. But in terms of composition, they are not typical of what we observed at Gale. Of course, we did not know that at that time. But when we went up, we saw that the composition was much different. And this location is actually not representative of the whole composition of the material at Gale crater. So we went from Yellowknife Bay here through this region where we observed mostly fluvial beds, and starting Paramp Hill here, and towards the clay unit, which was identified from orbit, we saw a lot of siltstone and mudstones with planar bedding, typical of lake deposits. Here in the Paramp Hill, in the Vera-Rubian Ridge, this one is more cemented, but you can still see the siltstone. And so in this sequence of 300-meter thick strata, most of the material which is recessive here is composed of this siltstone mudstone interpreted as lake beds. It's a huge pile of material. At the top of that, we observe some still fine-grained material, but with some cross-bedding. Cross-bedding is visible here with this layer, so at a centimeter scale, which is typical of either very shallow river deposits or shore deposits as you can expect, just nearby a lake. So we probably go out of the lake progressively here at this location. And between those two locations, we have intervals in which we see either from the images interesting mud cracks showing a drying out of the lake, at least in the location where we stood at that time. And also some intervals with interesting chemistry with brines, either magnesium sulfates, which is shown in this image with plot the magnesium against the sulfur. We have an increase in magnesium sulfates. You have also increase in halite in a few intervals, which shows that in some places we not only have a drying out, but also probably a role of evaporation, and the lake may have been shallow in these locations to explain these enrichments in salts. So staying in the chemistry, when you observe the different composition of the material here, all points correspond to one target from ChemCam. So 1 point is the average of 10 points, which itself, each 1 point is 30 shots. So it's an average of usually 30 shots on the same targets. And this average of all these targets along this column show you that the CIA index, which is the index of alteration, which is a good way to look at the alteration, whether it is open system or closed system. You can see a big difference from Yellowknife Bay towards the material at Parampil. Parampil start here, and all this material above Parampil is substantially altered. By substantially, I mean it's way above the value you had for the fluvial conglomerate, well above Yellowknife Bay. So it's not a closed system, like at Yellowknife Bay, where we think groundwater diagenesis may have been predominant. So it's really an enhanced alteration which is induced by open system. We don't know it was inside the lake or in the watershed and just transported some of the material within the lake, but at least it's still substantial, which doesn't mean it's tropical like on Earth, but just alteration was taking place. And when you look to the mineralogy, it's pretty consistent with this view, because with the K-mean result on XRD, all the green material correspond to clay minerals, and this clay, especially dioctahedral with aluminum 3+, iron 3+, type of neutronite or mormonite type of material. There is some hematite, I will come back to that. And the small corner with the light tone gray here correspond actually to the primary minerals. So the basaltic composition here is just 10% of the material. So it's really a very low proportion which remains from the initial rock. All the rest seems to be alteration or diagenesis, because you have also sulfates. So all of that is consistent with open system alteration and probably oxidizing condition at the surface. And I will also detail this point. That has been shown in Joel Urowitz's paper. There's also be shown in some of the ChemCam papers where we have a lot of manganese-rich phases which require oxidation, is that we need to have oxidation to explain both the clays we observe, the hematite, the manganese-rich material. And all of that, in Joel Urowitz's view, is that it's related to a UV interaction with the surface producing O2, which could produce oxidation, and whatever you have a stratified lake with more reducing material at the base, or if the material reduced is diagenic, does not matter, but at least at surface you need oxidation. So this is one view. Maybe there are other views to produce this oxidation, but at least this is surprising, because it's not the anoxic condition we could expect for an early Mars system, especially when we have greenhouse gases such as hydrogen and CO2. So on Earth, we know there were anoxic conditions with mostly reduced material at the surface. Why Mars is so oxidized at the surface seems to be the case at Gale Crater. So is it just something specific to Gale Crater interval of time? For instance, this morning, Bethany highlighted the paper from Robin Wordsworth in which there are oxidizing phases during the early Mars. Or is all early Mars oxidizing like this? I don't know whether Gale Crater is representative or not, but at least that's something to take into account into this system. Something else to take into account, which is a paper from Lauren Edgar, and Lauren Edgar is now an astronaut at NASA. So for the young guys here, you can be geologist and finish as a NASA astronaut. She has been selected 2 weeks ago. And in this paper, she worked on the laminar thickness of the material at Gale Crater and estimated the age required to deposit the 300-meter thick material has to be from 100,000 to 1 million years or even more. So this is really important time scale for us at the geological time scales. It's not a short scale as we expect, for instance, as J0. So one still caveat of that is that this is based on sedimentation rate on Earth, which is very low, typically 1 millimeter per year, sometimes a little bit more. So if you base on that, you find this number. Of course, we don't know what the sedimentation rate in a lake would be on Mars, but there may be no reason to expect that to be much faster. Okay, so very long duration for the formation of gale lacustrine sediments. Something else which is, I think, important to mention because it's not in any paper, and it's, at least for me, a big surprise, is that over all our material, we did not find any clues, any evidence from glacial, periglacial deposits. We know on Earth there is many ways to form glacial deposits, whatever there are in varves, dropstones, tillites, or diamectites, or whatever. Frozen lakes in Antarctica form sedimentary piles which cross the layer of ice and form either mounds or ridges. This is well known, and facies has been described in Frances Rivera paper recently. And none of that is visible. No cracks from contraction of permafrost, no specific sedimentary facies providing from any glacial, periglacial environment. So this is also true for the upper Murray that William will discuss in a few minutes. To me, it's a big surprise because the interval of time is so large, is so huge, that we should have had this kind of glacial deposit, and we don't see them. Whether they exist and we do not observe them, perhaps, it's always dangerous to take a conclusion from a lack of something rather than the evidence of something. So, but this is an important observation if true. If there is really no glacial observation, glacial facies within our sequence, this is meaningful. So to finish and to summarize, here is a kind of my take of the comparison between J0 and Gale. Maybe it's not still consensual in the team, but at least we can say that the thickness of the mudstone in J0 is much smaller than in Gale crater, and in Gale crater I just took the Murray formation. Again, William will summarize what we have above this formation. The fluvial river inlet is much higher discharge for J0 compared to the Murray formation. I did not show the conglomerates at Gale, but much lower, much smaller type of conglomerates. The alteration in J0, it presents, but because we have already been partly preserved in the first set, we can say that it's still either very cold temperature, and I say cold, it's still water, so around zero, or if it's a short duration, and it's substantially in Gale crater. By comparison, we have a full depletion of mafic minerals, not many minerals remaining. The duration, whether it's still debated, we have relatively short duration for J0, perhaps several thousand years, and at least 2 range of magnitude higher duration for Gale crater Murray formation, which is a substantial difference between the two. The age, as it has been shown by Cassie earlier, it's probably early Hesperian. It's not Noachian because it postdates the volcanic floor. And in the initial, in the selection of the landing site, it was sold as a late Noachian, predating the volcanic floor, but now it's clear it's not the case. And for Gale crater, it's usually still a question mark. It seems to be late Noachian or early Hesperian, which is still probably earlier than J0 delta, but still questionable exactly where it fits. In terms of paleo environment, we think it's perennial lake in both cases, but a glacial source or snow melt is really possible. For J0, especially to explain the big boulders, we need to have floods from some way, and one glacial input is an easy way to do. By comparison Gale, we don't see anything of that, no evidence of periglacial glacial deposits. We have episodes of drying out, and we have this thick material. So big difference between these two types of material. And I think I'm done. We stop here.
Very good. Professor Head.
Jim Head, Brown University. Excellent talk and great comparison. I'm wondering for the Murray formation, can you rule out that the 10 to the 5th episodes, or are you confident that that represents a continuous?
Yeah, so the question of GM is whether all the small beds, the laminae, which are many meters thick, represent just continuous perennial activity, or whether these are just episodes. Is that right?
Yeah, for example, 10 meters and then an interval of no deposition.
Yeah, the problem is to have 10 meters with just laminae which are less than 1 millimeter, which is the case here. It's 0.3 millimeter in average. So it's really, really quiet deposition to have siltstone. So if you want to deposit very, very slowly all this material, you need some time. So maybe the easiest way to do it is, if you want to something quick, is to have ash deposits, for instance, in a lake. In that case, maybe it's a little bit quicker than the fluvial input and some distal deposition of the mud. But still, even that on Earth is not so quick. So I think it's very difficult to have just small inputs in this lake from any episode of any, I don't know what kind of episode, because the matter is really very small grains, fine grains.
Okay, thank you.
Hello, I'm Taiko Hirai from Earth Life Science Institute, Science Tokyo. Personally, I support that the one of the most important difference between two sites is existence and or absence of the hydrothermal activity, or I mean the harsh and the high temperature alternation. So it's so abstractive question. Sorry, but do you have any ideas for the driver of the hydrothermal event between these these observation?
I did not speak about hydrothermal alteration, okay? We just have one example, maybe at Yellowknife Bay, where we have probably diagenetic because we still have low temperature minerals. And in most of the observations I show, we have no evidence of high temperature minerals. In comparison to what Kat is shown on the crater rim, we have a lot of high temperature minerals, such as the serpentine. It's probably a little bit higher temperature. At least it's very different from what we see here. So if there was hydrothermal, for instance, hydrothermal activity related to the impact craters at both J0 and Gale, we don't see them right in the sediments. The sediments really post-dates impact thermal, the role of the impact crater in terms of hydrothermal activity. I think by many million years, otherwise we would see it. We don't have much high temperature minerals in all this record.
Hi, very impressive. I have a question, maybe not for you, for J0 crater. In one of your slides, you mentioned that there might have been a speculation or a paper suggesting that the delta could have been formed in only 10 years. And I was wondering if it was a typo or if what is the scenario for such a fast accumulation? And secondly, in fact, is there a way for J0 crater delta to demonstrate that it cannot be the output of following a big impact, deluge-like climate for a few years, and then it will be that? You think you can demonstrate that it cannot be formed in a few years?
Yeah, and if you was really short, I think it would require to have only the boulder deposits to form in a very powerful fluids, continuous, and usually actually the duration of a few tens years is a continuous fluid, which we don't think it is. It's maybe arroyos, at least seasonal melt, not continuous. And we take that into account in modeling that is on the poster. And when you take that into account and the variability in fluvial regime, it's very rare to form that in 10 years. But you can form that in 1,000 years. It remains short at the geological scale. So if there is a kind of impact on the glaciers or any external activity related to explaining the seasonal melt or any melt of snow or of glaciers upstream, then maybe it's a way to form J0. What remains mysterious for me, J0 is probably, the fan is really the last stage of water activity in the region, but the Neretva valleys, which is the inlet valley of J0, is 10 times more, there's 10 times more eroded volume in Neretva than the J0 delta. So we probably just see the top of the iceberg, the tip of the iceberg, and we don't see the most of the sediments. But maybe it's decoupled, and what we see is just a late stage episode, and the episodes before, which formed main activity on the Everest, is not visible because it's buried below all the volcanic stuff that was showing Katie earlier.
Hey, any other questions? Thank you again, Nicola.
Okay.
Okay, and the final talk of this spectacular first day, William Rapin and colleagues will talk about Mars through the clay sulfate transition as recorded in Gale crater stratigraphy.
Good luck. Okay, great, thank you. So yeah, I will update you on the following, the upper section of what Nicola has just presented, because things have a bit changed since we were in the clay-bearing mudstones of the Murray Formation at Gale. First, to step back is that why it's appealing to study sulfates. You know, sulfates are a marker, a global marker on Mars of a change, we know occurring in the Hesperian related to Hesperian terrain. And here you have a few reference stratigraphies. We often forget that those terrains actually relate to several kilometer thick stratigraphies. You see here an example of sulfates in Melascasma. We map them everywhere. This is a general positioning of them in a time-related sequence. And so the big question here has been since what environment did they record? And unfortunately, we cannot stay in orbit to know, so we have to land to get data from and get answers from those questions. What were recorded and where are all these sulfates coming from? And luckily, that's right where we landed assets on the surface. We have the luxury of using all the rover fleets and data to study that transition. And in particular, here I'll show data from, I can say this way, from Curiosity, which gives us a pretty large stratigraphy now. But the first rover to land on sulfates, sulfate-bearing rocks, was Opportunity in Meridiani Planum. And we expected something before landing, but that's what we got. We identified here like aeolian deposits, mostly cross-bedded sandstones and planar sandstone, but loaded with sulfates, sulfates everywhere, and jarosite everywhere, which is a marker of extremely acidic water. So that was a picture that Opportunity provided in Meridiani Planum, but it's limited by only 7 meters of stratigraphy for a unit that is supposed to be large. So when we went to Gale, the sulfates were supposed to be at the end of the mission, so we know we would expect something to relate that to Opportunity. So, but in Gale, really it's different setup. Here you see an overview of that. The clay sulfate transition is right at the base of that mound forming. The slopes get suddenly much higher when we arrive here at the base here, and really we have nearly 800 meters of strata to explore here, so much greater than 7 meters at Meridiani Planum. And what did we see when we get there? Well, something a bit different. Here you see the cation against sulfates, which is measured by the chemical analyzer we have on Curiosity, the ChemCam, which uses laser-induced breakdown spectroscopy. And it's pretty useful because we can sample anything with any roughness. So in particular here, what you see is that what is bearing the sulfur are those nodular forms in the host rocks, which are pretty rough. But we sampled them extensively with ChemCam, and we saw that those are bearing most of the sulfates in comparison with smoother bedrock here nearby. And there is quite a diversity of it. So in comparison, you would see the increase is similar to what we've seen in the Burns Formation, but actually in the Burns Formation was everywhere. Here is localized in nodular growth, which is a key difference. And how it looked like, the transition is really clear. When we arrived from the clay-bearing unit here below, into the sulfate-bearing unit, we really started to see those sulfate nodules popping up. It's quite striking here, the change in chemistry. You see the sulfur measured has elevation here. So those nodules arrived in a viable density, but they were clearly there when we get into that transition area. And so here you see them in stratigraphic order, so you have that overview, and the sedimentary fabric changed. Really, we went into a transition in another stratigraphic member, crossing that boundary. And the key thing that changed here is that the sedimentary fabric is consistent with large-scale cross-bedded sandstone. We had struggle finding the actual sand grains, but the structures are really consistent with those large trough crossbed. Here you see them in decameter scale even. So those are diagnostic of the passage of dunes, large dune, three-dimensional dunes, likely Balkan, climbing on each other and depositing those large sets. But we also see other things. We see smaller scale cross-bedding here, and we see those lenses which surprise us quite a bit. In fact, we didn't see only transition from lake that Nicolas has described to just dry. We've seen those, zooming on those lenses, we've seen wet environment here. So those small lenticular-shaped bodies are actually the fabric we've identified. There are those wave ripple laminae, so they form symmetrical wave ripple bed forms, which actually are similar to the one you find in shallow water that imprints the sediment surface when the waves have an oscillatory motion. You obtain those symmetrical forms of ripples right on the sediment surface. And there they got preserved. We've also seen a very impressive example of that at this transition here, which is a huge marker, a regional marker. And we didn't know what to expect. And when we arrived there, this is what the outcrop looked like. And those are published now by Mandro et al. I should have added the reference. But, and they are a clear indication, I think the clearest indication we have on Mars of an ice-free lake. You cannot form those ripple marks if the lake is covered by ice, because the wave motion induced from the wind would not imprint that oscillatory motion and create those ripples. So quite an evidence here for ice-free bodies of water right on the surface preserved. And so one of the things we've done is look at that stratigraphy. We have the luxury of having pretty large buttes to look around. Now we are in those canyons. And here you see one example of soft mountains, 100-meter thick. And we can look at the architecture of strata here this way. So more extensively, we look at the features. If you zoom in on those, you can look them in high resolution using our cameras. And we see those lenses here in the spot within the strata. To show you some example here, on the top here is a planar bedded section topped by this erosional surface, which is where we found actually the ripple marks further when we arrived with the rover. And here you see again those lenses that are, the fabric of those lenses, the sedimentary structure, are much smaller scale cross-bedding, which actually some of them also show the ripple marks. And we think those are diagnostic of fluvial activity here and standing bodies of water. So the overview of that survey at GEAR, we can do that on several. You look at several buttes, you look at what you've seen along the rover path, and you assemble that into the stratigraphic architecture. So we see that clear change. You know, we were in damp, wet environment below, and we went into those suddenly dry aeolian strata while sulfate nodules came up. And then we are back into something wet. This part we call it wet aeolian. You have to imagine this is consistent really with large-scale dunes, but the interdune has ephemeral, intermittent fluvial activity, even ponding of water. And at the top of that, you have really regional deflation, so suddenly becomes erosive instead of aggrading. And on top of that, a lake, a pretty large lake, ice-free lake, on top of that unit. So it's not a uniform change of environment. Here you see you can try to guess the height of that water table through time. and if the aeolian environment is depositing or erosive. You can start to construct that story. And it seems really typical of aeolian sequences on Earth, where actually the sand budget and the water table, in a local scale, they relate to each other, because the rise of water table will actually make the sediment stick to the surface. And so if you exhaust that sediment supply in the aeolian setting, then they relate to each other. When the water table rises due to climate forcing, then there is suddenly less sediment to feed into the system. And they form this stratigraphy. So what we see is kind of typical to what we see on Earth. There are these gaps in time, and you obtain either a bypass or deflation, depending on the severity of that climate forcing. So this is a bit of a cartoon. They don't have to be that periodic. It's a bit of a chaotic process, but they are related to each other. And that's more or less consistent with what we see on Earth. The thing that we don't that much see on Earth is really those nodules of magnesium sulfate, calcium sulfate, that's loaded with sulfates here. What's interesting is the distribution of those nodules is odd. And I think we have there one of the evidence that, the key question is, when did these nodules form? To know where the sulfates come from, we have to know the timing of that nodule formation. And to me here, because the dry aeolian deposition doesn't have any nodule, but suddenly when we see evidence, like sedimentary evidence for surface water, the nodules pop up in the strata everywhere. I think this is evidence for that the nodular formation tracking the water table instead of nodules forming into the most porous aeolian part. So to me, it supports an early evaporitic origin. And so we are having saline water table oscillating. When you have purely dry aeolian deposition, that water table is too low, so evaporation is not efficient. And when the water table rises to the surface, you see ponding, you see fluvial channel time to time. You have fresh water feeding, but the water table remains saline, extremely saline. And when it reaches the surface, when it dries during dry period, then nodules form because it concentrates and saturates in the shallow subsurface, sediment surface, so imprinting those nodules in the mass of the sediment. And I will show you now, to finish, a couple examples that are striking, really been surprising us. When we arrived, we saw those nodules. They were organized, and so we saw diversity of those. And those at that location, they were organized, forming a polygonal pattern that really was unlike anything we've seen before. And actually, they form even this step lithology. So this shows you there are like a vertical pattern that is penetrative in the sedimentary rock. And we sample those. We know there are calcium sulfate, and we could map those hexagonal shapes. What we think is that this is a type of columnar soil. It's a salinization process, which on Earth farmers hate, because really plants don't really grow well on that type of salty ground. But on Mars, we were quite happy to find that, because in that model, that means that they track really the high frequency sort of cycling of wetting and drying condition, but in a seasonal manner. And so it's the first time we have that tangible evidence, according to that model, that the hydroclimate fed into that wet and dry cycling. Clearly, you cannot make columnar soil in a hydroclimate that is purely driven by volcanoes or impacts. In that interval of time, to produce that soil, you need a hydroclimate regime feeding into wetting and drying. Another surprising before is the siderite, where we were at marker band. We found siderite where we're supposed to find sulfates. We found that with X-ray diffraction. It was a big surprise. We did not expect that from orbit. We think they form early diagenetic in the shallow surface. And I'll be quick over time. We've also identified that it's extremely hard to find carbonates using purely the laser ablation technique. But it's the first detection, the positive detection we're working on now, validates the presence of siderite in a lamina. And it means if we see it, there is a lot of it. And here we can say more than 50% in that. So we see early diagenetic siderite, and we see this lamina of nearly pure, not nearly pure, but really rich, extremely rich in siderite here. And if that is a lacustrine lamina, because it's extremely thin, it's consistent with that lacustrine deposition, that allows for a modeling of coupling with the atmosphere, like atmosphere coupling, to explain how the water column of the lake could have precipitated siderite. So we hope to do that. So to finish, what we found at Gale is that sulfates clearly are no longer the marker for the end of habitability that we expected. They tell a really different story. They are associated with evidence for high frequency with dry cycling. It's important for prebiotic evolution. And we also see evidence for climate forcing, those large aggregating sequences and then deflation and then again aggregating. These are significant forcings on the climate that are recorded in Gale over hundreds of meters of deposition. And we see carbonates. The sulfate-bearing unit is becoming the carbonate-bearing unit in some way. So even if those is influenced also by late-stage brine, we have piling evidence that everything is stratigraphically controlled by varying environments that are recorded in Gale. So I would say that there is even more to come. We still have hundreds of meters to climb, and we are ready to discover more. So yeah, happy to discuss.
Thank you. Okay, this paper's open for questions.
Hi, Thanos Gladaris here from Purdue University. I was really interested in comparison with the Burns Formation at the beginning, and you mentioned like only 7 meters of stratigraphy was like explored by Opportunity. I was wondering, did Opportunity ever find anything that might have been excavated from underneath? Like, were there any like Noachian, float rocks, clay-bearing float rocks that could help you address this clay sulfate transition at Meridiani? And if Opportunity never found anything, what does like the orbital data suggest for that area?
That's an excellent question. I know Opportunity only from the distance, but the stratigraphy was accessible from the rims of craters in the plane of Meridiani Planum. So I assume there wasn't a basement available other than the stratigraphy observed. I think from the other data, I think what you're pointing to is indeed how do we relate what we find in Gale to other places, and that's I think a big piece of work that needs to be done. Is at Gale where we have Curiosity, we have Crism data set, and as you see, we did not expect siderite at all, and now we find siderite. So how does that fit into the story in other places on Mars? Do we have siderites everywhere there are sulfates? So we need to investigate these possibilities now and what it means for sulfates on Mars more globally.
Thanks.
There's no, by the way, we didn't see any of that opportunity. And the ejecta blankets are all planed down and eroded away, so we wouldn't have seen it in those. Other questions? Yes?
Question for you and maybe Nicolas or whoever, and you. Know that we have learned a lot from the bottom of Mount Sharp and so on. It's a very naive question based on Crism data or whatever. Do you think how high do you think they were? The Gale crater was filled with water or whatever. How was it deposited? Can we extrapolate a little more, a little better than a few years ago?
Yeah, that's a good point. And so as you've seen, only the bottom part have the most evidence for water deposition. There are still some right now, but we are still at the bottom of Mount Sharp. Like we didn't even have a kilometer high. As you see, there is aeolian processes now. So once you go from lacustrine or fluvial to aeolian, then it's not gravity driven. Winds can go upslope, which water won't do. So the rest of Mount Sharp could be formed by aeolian processes, and so Mount Sharp does not need to be entirely filled to produce the remaining Mount Sharp deposits. I think Edwin and others also had a great paper of how mound-forming unit can mount on top of each other to fill the crater without filling it entirely. So the basinal parts are the one that will be having most of the imprint of liquid water.
at the top of Mount Sharp is higher than the average crater rim.
Yeah, I know that, but my question is, what is your best guess? How high did the water ever get?
Well, we see that lake. The marker band has a lake, but it could be perched lakes within the sediment. It's a shallow lake on the marker band.
Marker band doesn't extend all the way around the edifice, so.
Right. Could be series of lakes.
Other questions? All right, let's thank our speaker again. Thank you, William. Francois, do you have any announcements? I think the doors open at 8:30. Session starts at 9. We'll continue on early Mars environment. We'll talk about clays tomorrow. So thank you all for a great day today, and thank you again, Francois, for bringing us all here.